Good. Very good. All right, folks. So here we go. We're going to continue our review of Algebra 2. Okay, and Algebra 1, and maybe even prior to that with this, kind of stuff. But anyway, you'll see get the idea here. All right, we're looking at functions today. We're going to define a function. We're going to talk about the graphs of some basic functions. Okay, that's that paper that I gave to you there. And then we will also talk a little bit about transformations too. Okay, so that's kind of the idea here. All right. So, a function. Yeah, we're good. Yeah, please come on back. And we're just starting the notes, so you're perfect timing, bro. All right. A function from a set A to a set B is a relation. Okay. That. I want to pause there real quick. So, the word function, we get kind of tossed around and we get so used to it because pretty much everything we do in our math classes, right, pretty much everything we work with are functions, okay? And so we kind of like lose sight of this thing, of something being a function as being special or at least unique and set apart from like other things, right? So for the most part, everything we work with is a function, and so it's kind of like we get lost. We're like, oh, function, that's just the thing that we have, but we kind of lose like, well, there are things that are not functions, right? So this word relation is actually a bigger umbrella term, okay, under which function is like a subcategory. So relation means relate is what it is. It relates, two things to another somehow, and then a function is a specific kind of relation that assigns. Okay. And does anyone remember what makes a function a function? Jeff, you want to take a stab at it here?
For each y value, there's only one, or y value, there's only one x value, right? Or is it the other way around?
Other way around. Mm-hmm. For each x value is assigned to only one y value. Right, and so yes, that'll show up. Yep, we're going to talk about that in a second too. That shows up graphically, with a vertical line test and stuff like that. So yes, that assigns each element, and we'll just say x. Okay, and when I say element is just a single member of that set. Okay, so an element x from set A. Okay, to one element y in set B. Yeah, so typically, right, with mathematics, right, with stuff that we do, the set A is all of our x values, set y's, or set B is all of our y values and stuff like that. Yeah, each element x from set A to one element y in set B. Okay, so yeah, only one element y.
A one-to-one function has both, right?
A one-to-one function, yeah, then the opposite is true. I guess let's
both
the converse. Yes, one element x is assigned to one element y. Mm-hmm. So we can say in shortly, every x goes to one y. Okay, every x matches to, goes to, is paired with, relates to one y value. Okay, but that means certain x's can go to the same y value. That's okay. All right. So function testing. That is determining whether something is a function or not, right? And this is again pretty straightforward, reminiscent of what you've done before. Okay, I'm going to call this one algebraic. Okay, algebraically we can test kind of thing, although I don't know, how important that name is. We're just going to check to see, like literally just look at the function. Check to see that each x is assigned to one y. Okay. And so we'll just do 2 examples here real quick. Is it a function? So we'll do 2. Okay. And we'll start with a very basic function, or not function. I think we'll start with a very basic relation, I guess I should say. Okay, so we'll just do some ordered pairs, right? Typically, we don't, this is like so simple. This is going back to like maybe even middle school or something like that. I don't know. But, these are the most basic kind of relations we have where it's just a set of coordinates, inputs and outputs, x values and y values there. Okay, so I got 4 coordinates there. But this is a relation, right? It relates these first numbers. These would be like in our set A, right? Or the domain, we sometimes call that too, right? And then 6, 5, 9, and 5, those are part of our range, or in set B here, right? So we have an element x from set A matched with an element y from set B. X, y, x, y, x, y. Okay? So, does every x get paired with only one y value? Here. I hear yes. I hear no. No? Okay. So let's take a look. Does this x -1, does it get paired with only one y value here? Just a 6, right? There's no other -1s that get paired with a different number. Okay? The 2, it gets paired with only the 5, right? There's no other 2s here in the x values that get paired with a 5. Okay? Or another number besides 5, I should say. 0 gets paired with 9, 3 gets paired with 5. So, some people might look at this and say, oh, Mr. Wade, that y value repeats. That's okay, because it's every x value matches to only one y value. So the 2 goes to a 5, the 3 also happens to go to a 5, but that's okay. Okay, because they're different x values there. So yes, this is a function. All right. Let's try a second one here. Bless you. Bless you again. So, second scenario, same question though. Bless you, what did we say? Function or not? No? Okay, why not? 6's go to -2 and to 1. So that's exactly right, okay? This 6 is paired with a -2, this 6 is paired with a 1, and so no. Every day? I don't know. I think it's either Greer or Patrick. One of those two. So I don't know. Yeah. They must be doing some sort of like reading circle or something like that, and everything has to get moved around. So. Okay, so next, graphically is the other common method that we use to identify whether something's a function or not, right? And that is what Jeff hinted at earlier there, the vertical line test.
So basically a function is a relation in which each y value is unique.
Well, let's see, unique y values. Well, again, in this situation, right, the 5 y value was repeated. That was okay. And that's okay that different x values go to the same y value. It's that we don't want the same x values.
So each x value is
unique. Yes, although you can have, so for example, if I had like 3 5 show up again, that would be okay. So if I had like 2 3 5s, that would be okay.
At the same point.
Exactly. Yeah. So I don't, right.
Each x value is unique.
I think so, yes. Is uniquely paired to y. A y value.
Each x value is
yeah.
unique.
So, vertical line test, if, and this is like hard, like it's easy to know what to do, but for me it's always hard to write it out, but forgive me if this is like too much, but anyway. If a vertical line intersecting any part of the graph of the relation, Okay, so again, vertical line test of a vertical line intersecting any part of the graph of the relation intersects more than once more than once. So 0 points of intersection, okay. 1 point of intersection, okay. More than one, then the relation is not a function. Okay, not a function. Okay. Or in simpler terms, if you can draw a vertical line through any part of your function and it hits more than once, not a function kind of thing. Okay? And that shows up here, even in this situation right here, right? So if you were to take these two relations that I showed you there from the first two examples that we did, if you were to plot those points, you can kind of see what's happening, why that vertical line test kind of works, right? So if I just really quickly here sketch, like a coordinate plane, and let's see here, I'll try and plot these. Ooh, 0, 9. Okay, well, I'll go count by 2. So 2, 4, 6, 2, 4, 6, 8, 10, like that. All right, so we've got, let's see here, -1, 6. So 2, 4, 6, like that. 2, 5, 2, 2, 4, 5. 0, 9, 0, 2, 4, 6, 8, 9, and then 3, 5, 2, 3, and then 5 like that. Okay? You can see, right, that any vertical line you draw through this point, through this point, through this point, or through this point, right, that vertical line would only intersect our relation at one point there. And so, function, right? It works.
Circles are not functions.
Yes. But now I take a look at the second one, 6, -2. Let's see here. So 2, 4, 6, and then you can eyeball that right there. And then 9, 3, 2, 4, 6. 8, 10. 9, 3. Something like that. 8, 2, 8, 2, and then 6, 1. Okay. There you can see that vertical line would intersect 2 points there, right? This one's okay though, this one's okay, but since it fails here, the whole thing fails and it's not a function. Okay? So that's the idea there with that. You can see it visually. All right. It's just kind of a visual representation of that exact definition that we talked about earlier. Okay. Questions on any of that? All right, so let's take something like our circle. And if you have your graphing calculators handy, you'll want to get those out here. Okay, if you don't, that's okay. You can just follow along up front. But let's take a circle. Let's take a circle equation. Okay. Now let's graph this thing. All right, let's graph it, but not sketching it. Let's graph it on our graphing calculators. Okay, just because we can. All right. In order to graph this thing on our graphing calculators, though, is it ready to go as it's currently written? Can we graph that the way it's currently written there? No. Okay, what do we need to do to it in order to be able to graph it? So you don't give me the exact steps. Like, what's our ultimate goal, though? Yeah. Yeah, we need to solve for y, right? Okay, which would then start, and I think, Brendan, you were starting to say there, subtract the x squared from both sides. Is that what you said?
Yeah.
Yeah, okay, I thought that's what I heard you say there. So 16 minus x squared. That's right, so far so good. And then what should we do next to continue to get the y by itself here?
Square root it.
Square root both sides.
So y minus 2 equals 4 minus x.
Okay, so pause right there real quick. First of all, since we're taking the square root in an equation setting, what do I need to put in front of the square root now? plus or minus, right? It could be positive, could be negative kind of thing. Then, can we simplify the square root of the quantity 16 minus x squared? Can we simplify that? Can you break a square root up over subtraction? No. So we have to leave it quantity 16 minus x squared like that. We cannot simplify that to be 4 minus x. Okay? It's not mathematically equivalent.
Oh.
Unfortunately. If it was 16 times x squared and we square rooted it, then you could do 4x squared. Okay. But since it's got the minus or a plus, you can't break a square root up over a plus or minus. It's one of those like funny math phrases or like those like little brain twisters. You can be like, the square root of a sum or difference is not equal to the sum or difference of the square roots. Okay, kind of thing. Anywho, last step, what do we have to do still? Add the 2. So we'll have y equals 2 plus or minus the square root of 16 minus x squared. Okay? And really at the beginning, we kind of already knew what the answer to this was going to be, right? Is a circle an example of a function?
No.
No, right? We know we can picture a circle in our brains. A vertical line will definitely hit it more than once if it goes through it at all, kind of thing, except if it's tangent on the ends there. But you can also see it algebraically here too. Pick any random x value that you want. Well, let's not pick anything because we could get an imaginary number. Let's just say we pick like 2 here, right? 2 squared is 4. 16 minus 4 is 12. Well, the square root of 12. And we're going to take that 2 and we're going to add and subtract root 12 from that 2. Which means our y values, right, from the single x value of 2, when I plugged it in, we're going to have 2 y values because that plus or minus. So 1x is going to be paired with 2 y values. One where it's 2 plus the root 16 minus x squared, one where it's paired with 2 minus. And so also algebraically you can see here, that x value we plug in is going to get paired with 2 different y values, depending on whether we add or subtract there. But let's go ahead and graph this too. Okay, just so you guys can see that you can graph these circles in your graphing calculators. We'll go to y equals, okay, and we'll type in the 2. And then how should we handle the plus or minus in our graphing calculators? Does our graphing calculator have a plus or minus command? No, it doesn't. So, yeah, so what do you mean by do both?
Just 2 separate lines.
Exactly. Yep, exactly right. 1 in y1, we'll do 2 plus the square root of 16 minus x squared. And in the bottom, we'll do 2 minus the square root of 16 minus x squared. Okay? Just like that. And then there's our circle.
Wait, why isn't it finished?
So that's part of the, I think it's part of the graphing calculator, how it like does things. If you were to like zoom in on those areas, it would actually get closer and closer and stuff like that. But it's just kind of like the algorithm, I guess, this uses. You can see here the resolution for these screens is not very high, right? Like you can literally see the pixels. All right, like these little tick marks, that is an individual pixel in your screen there. So that's why it kind of doesn't graph really nicely. Okay, it's very low resolution. It's also kind of weird that the shape doesn't really look like a circle. But why is that? Why does it look like a football? Yeah.
It's because like the scales are different for the x and y.
Yeah.
It's like really weird.
Our screen is a rectangle. Okay? The default window for a graphing calculator, if you go to window here, the default window is from -10 to 10 on the x-axis, -10 to 10 on the y-axis. But if your x-axis, which is the kind of the width here of your screen, if your x-axis is 20 and your y-axis, which you can kind of think of as the height, is also 20, well, this 20 will be stretched out on the horizontal as compared to the y-axis, which will not be as stretched out. Or you can think the y-axis will be shrunk in compared to the x-axis. There's actually a command on the calculator to fix the screen so that it's like square. And if you press the zoom button and you go down to number 5 there, zoom square, it adjusts your window so that the x-axis has more values on it than the y-axis does, so it kind of makes it now look more square. And there's your circle. Okay, and again, it would complete if you were like zoom in and stuff like that too. Okay, but there's that. Okay, super important that you're also comfortable with your graphing calculator when it comes to calculus. Okay, again, if you're planning on taking calculus next year, or even statistics too. Okay, you really want to be comfortable with that graphing calculator. But especially in calculus, you do a lot of like analysis of what you see on the screen and stuff. So you want to make sure you can type things in correctly, and then also, see the screen and manipulate your window and stuff as well. And we'll get more practice with that as we go along in this class too. So, anywho, not a function. All right, there we go. And Ro, I can get you a copy of these notes that you missed here too, but that's not too bad, okay? Just because we're going to move on to the next page here. Yes and no. It's review, but we'll get you caught up. All right, so let's get out those papers that I handed out here. We're going to talk about a few of these basic functions, okay, or function families, we'll say, or something like that. Okay, function families. All right. So we bother learning some of these basic function families. Question.
Do I get a paper?
Oh, I guess I should give you a paper, yeah. All right, here you go, Rob. We bother learning these because we want to become familiar with their thing. We want to become familiar with their characteristics, and it can be helpful just to have a picture in your brain, right? When you know that you're graphing the equation of a line, you have a picture in your mind of what a line looks like, and so you can kind of visualize it real quickly and stuff like that. So it's helpful for sketching too. The identity function is merely the function f of x equals x, okay? F of x is equal to x. Okay, or 1x there. Interesting. And, this graph will be the graph of a what? A line with slope of 1 and y-intercept of 0. There we go, yeah. So something like that. Again, just a quick sketch. Okay, just a quick sketch.
So that's a linear function?
Yep, linear function. Because you can then transform that to match any other line. You can shift it up or down, left or right. You can change the scale there, or the scalar in front of it kind of thing, and make it, get the right slope and things too. Okay? We'll worry about domain and range, though, later, so we're not going to worry about that right now. Absolute value function. This is f of x equals the absolute value of x. And this one gets a little bit more interesting.
That one's a v or a...
Yeah. Or an upside down v.
Upside down v.
Yeah, right. There's not really a name for that shape. So yes, so it's like a parabola. Yes, it's like a parabola. It's got like a
But it's
vertex.
a straight edge parabola.
Right. So if you think about, again, the absolute value function, okay, is closely related to the identity function. In fact, they're identical, except the absolute value symbols are around the x here and the absolute value where they are not there. What does absolute value do to a number? So, yep. Go ahead, Natalie.
It's just the distance it is from 0.
Right, that's the exact definition. And can the distance ever be negative? No. So it's going to make anything that's negative now it's going to become positive. Anything that's positive will stay positive. So if you look over here at this graph, what part of the graph is positive already? The right-hand side from the axis. So that part will remain the same as the identity function. Exact same. The part that's negative over here on the left-hand side, what's going to happen to all those values? They're now going to become what? Positive. And so it kind of reflects, this piece reflects over the x-axis there, and that creates that kind of V shape that we're used to. Just like that. Okay? So what you can use that for now is we can now transform it. Okay, now we can use that and transform it, move it around. We'll talk about transformations on the back of this paper, but there it is. Okay? This allows you, that kind of thinking can allow you then to do the absolute value of other functions too. Okay, so we're not going to worry about those right now. That's the one we'll stay focused on that one. All right, square root function. Square root of x. Square root function, square root of x, we'll start here at 0. And this one I'm going to add a few tick marks in because it is helpful to have some of those. Okay, so square root of 1 is 1. Square root of 4, notice there's no plus or minus in front of this one. Okay, we're just keeping the positive square root of x there. No plus or minus. That way we're still able to have a function, right? If it was plus or minus root x, it wouldn't be a function anymore. And of course, the square root of 0 is 0. That's right. 0 is a perfect square. Okay, so something like that. Okay, so the square root squaring function, I don't know, some of these
Quadratic.
phrases I should maybe update. But yeah, quadratic function, okay. We'll just talk about f of x equals x squared. That's your parabola, right? And again, I'm not going to worry too much about these points here just because I think we all get the remember what a parabola looks like. Okay, just like that. Okay. Is this a function, squaring? Is x squared?
Yes.
It is, right? Okay. Some y values get repeated, right? But every x goes to one y value. Every x goes to one y value. All right. Next one we'll do is cubic. Okay, x cubed, and that looks something like this. And again, I'm not too worried about getting those points down so precisely, but there it is. And we'll do one more here. We're not going to do sine and cosine just yet. We'll hold off on that until we get to our trig unit section. Rational function 1 over x. Okay, 1 over x. And this is going to look, well, on the y-axis here, we're going to put a dotted line. Okay, because that's when x is 0. And if x is 0, what are we going to end up with here for our y value? Or what's 1 over 0? It's error, right? Or undefined. The calculator will say error. We're going to say undefined. Okay? So it's going to look something like this, though, rational function. We also have horizontal asymptote at y equals 0 as well. Okay? And again, we can transform that, too.
And some rational functions can also be a linear function with a point of discontinuity.
Yes, and we will look at that in more detail later. Okay? So there those are. Okay? And so that gives us a good idea of the basic kind of shapes, and then from these you can create, varieties of these or different versions by using your transformations and things too. So questions on any of this so far? Pretty straightforward stuff. Quick review of Algebra 2. Okay? Because in Algebra 2 I feel like you spent like units on each one of these separately. And we'll come back and talk more about these in depth too some. But for now we'll just stop there with that. All right, last bit. Let's talk about transformations. On the back here. Okay, for all these transformations, we're going to start with just the fact that c is greater than 0. So we're going to have this positive number c. Okay, and then we'll do some transformations here. So, if you have a function, f of x, like one of the ones on the other side there, or some other completely different function, okay, if you take that function f of x, and then you put a plus c, you add c to it on the outside there, the new result, so f of x, add a c to it, the new result of this function will be what kind of transformation? Up, shift up how many units? C units, yep, shift up C units, okay? Or in geometry terms, a translation, up 3 units, up C units, I should say. And so, of course, then if we wanted to go down, we would do f of x, what? Minus c. Yep, and that's a shift down. Okay. Whoop. Putting the c inside the function. So f of x plus c. So every x in the function gets replaced by x plus c. What kind of resulting transformation is that?
It's a horizontal one.
It's a horizontal, and yes, it is left. It is left. Very good. It is left. So shift left. C units. Okay? So it's like kind of counterintuitive there. All right? The best way I can kind of describe why adding c results in shifting everything left is because if you think back to your original function f, and you reached a certain height at a particular x value, right? Well, if you take that particular x value and you add c, you're now kind of like moving further along, And so a lower x value, adding that c to it, will result in the same height, the kind of that future height almost kind of thing. It's kind of hard to describe, but the idea is it shifts everything left because these x values, you're gonna arrive at those x values earlier because you're adding c to it now. So it kind of moves things to the left. Okay, and I don't know if that's a good description or not, but it's a little bit weird. So then, of course, if f of x plus c shifts it to the left, then f of x minus c shifts it to the right. Yes, we know our opposite. Shifts right, c units. All right, two more transformations here. If we throw a negative in front of our function, okay, what will that do? Reflects, yeah, that's right. Any more detail than that? Over the x-axis, that's right. Okay, because think about it this way, right? Originally, you would have a point x comma f of x, right? X comma f of x, or x comma y, x comma f of x for your point. If you then take all those y values and you make them the opposite, right? You make them the opposite of what they were, then that results in reflection over the x-axis there. Okay. And then if we throw a negative inside like that, yeah, exactly. It's a reflection over the y-axis. Axis. Okay. All right, so I'm going to do two examples of this, and then I'll have you guys try one, and then we'll get you started on the assignment. Okay, that'll be that. Okay. So two together here, and then one on your own, and then you get started on the assignment. All right, so directions, sketch the graph of g of x. All right, so let's say our first function, our first g here, g of x, is negative x cubed minus 5. Okay, so what kind of transformations do we see here? Shift down 5. Reflection over the y-axis. Yep. And so we will, I suggest you do the reflection first, just to kind of make it easier for yourselves there. So, okay, and I'm just going to count here down. 1, 2, 3, 4, 5. Okay, so that's where our new vertex will be. Although I don't know if I want to use the word vertex there, but kind of like the center point of the graph. And then it's just going to go down from left to right as opposed to up. Okay, like that.
Is it x cubed? Oh, it is.
It's x cubed, yes. It's x cubed. So something like that. You can put, more points on the x-axis there if you want to, and actually plug them in and check and see. That's your choice. All right, but again, for a sketch, I'm okay with just doing this. Okay. Questions on any of this? All right. Yeah. Okay. Let's try another one. Negative quantity x minus 2 squared plus 1. Okay. Negative quantity x minus 2 squared plus 1. Okay. So what's our parent function going to be here? X squared, right? Our quadratic there. What kind of transformations are we going to have happen here, though? What happens?
Shift up 1.
Shift up 1. Reflect over the x-axis in this case.
And also shift Right.
And then shift right 2. That's right. Okay, very good. Yep. Okay, so here we go. So again, I think if you take care of the shifts first, that kind of makes it easier. So we'll go right 2, up 1. So again, 1, 2, 1. So there's my new vertex. And yeah, since we have a negative there, it's going to go down. So it looks something like that. Okay. Again, if you want to, you can identify more points to get an idea there. But that's again a good sketch of it at least. You get the idea. Okay. Alrighty, and I'll give you guys one to try here. So you all try this one. G of x is equal to the absolute value of x plus 3 minus 3. Okay, go ahead and sketch that real quick. So that means we should shift. And that means we should shift. Yes. You got one of the transformations, right? There's an x plus 3 and then a minus 3. So what does this transformation mean? It's in with an x, so it's like a left or a right transformation. And then you want to do the down. Yes.
So what kind of transformation is that?
Left, great. Yeah. Jeff, you get this okay?
Yep.
Yeah, looks good to me. As long as you know, yeah, that's like a 3 and a 3 there, or whatever, that's fine. Okay, cool. Something like that. Okay, the vertex moved to -3, -3. Okay. Questions there on any of that? All good? Okay. So, your assignment then, I'll get you started on that here.